Hello everyone, welcome to another Physics 30 example set. This time we're in Unit 6, which is Nuclear Theory, and Lesson 6, which is all about particle tracks and particle accelerators. So here's our first example. We have a particle track image. Let's just take a quick look at this first. This is our region of interest, and we've got these black dots here indicated by the capital letter B. So these black dots represent or the direction of the magnetic field, and based on sign convention, this means the magnetic field is coming out of the page. We then have four numbers that represent the different parts of the particle tracks. This number 1 is a dashed line, which represents a track that's not visible, or the direction of a particle, but would not be observed in the cloud chamber. And then we have 2, which is a spiral, which is the radius is getting smaller, and the direction is counterclockwise. 3 is exactly the same spiral, just going in the opposite direction, it's going clockwise. And then 4 is a thicker particle track, and it's got a much bigger radius of curvature, and it's also clockwise. So the example is getting us to think about 4 types of particles. Let's state those here now. So we've got alpha particles. Actually, I'm going to use black. Alpha particles right here, which is 4 nucleons, so 2 neutrons, 2 protons. It's getting us to think about beta particles, there would be 2 types, of course. There would be beta negative, which is an electron, and there would be beta positive, which is our positron, and then lastly we're going to think about our photon. Okay, so let's think about our alpha particle first of all. This guy here, it has a mass which is 4 atomic mass units. Okay, now if you're not totally okay with values, you can look at your data sheets, but a single proton is 1.67 times 10 to the negative 27 kilograms, and an electron is 9.11 times 10 to the negative 31 kilograms. So we can talk about an order of magnitude of about 4. In fact, if you did a quick calculation, you'd realize that there was a difference of about 1,800 times. In other words, the proton is nearly 2,000 times more massive than an electron. But of course, an alpha particle has 4 nucleons, so we would have to multiply this 1,800 by 4. In other words, the alpha particle has approximately 7,300-ish times the mass of a beta particle. So it's significantly more massive. And so if you think about when something is in circular motion, as it's rotating around, the bigger the mass, the more inertia it has, and therefore the less it's going to respond to a force. And in this case, the force is the centripetal force, which is also the force magnetic. And so it's responding much less to that, and we can see that, and we can think about that intuitively by the amount of curvature. So it's intuitive to look at this initially and just see, and in a moment we'll do some calculations or some algebra to figure this out, but it's intuitive to think that a more massive object moving is going to take a wider turn. In other words, the radius of curvature is going to be much more massive. So I'm inclined to think at the moment that the alpha particle is track 4, based purely on the radius of curvature. It's got a large, I'll put that track 4, it's got a large radius. Okay, let's also do our hand rules, because of course the alpha particle will have a plus, it'll have a plus 2e charge, and so we can get our right hand rule out here, because it's a positive charge Our thumb is going to go to the right side of the page. Our fingers are going to point upwards, and therefore the palm of the hand is pushing downwards, which does match the direction of curvature. In other words, in this particular particle track, in this particular particle, a bubble chamber or cloud chamber, a positively charged particle moving from left to right will experience a force downwards, and therefore the curvature will be clockwise, just like we see with track 4. So this again is just verification that it's a positive charge, and therefore we're going to use our right hand rule. And so I'm thinking already that track 4 is the alpha particle. In addition to that, we also see a thicker track. And that's indicative of the size of this particle. It's, like I said, it's 7,300 times the mass. It's also got double the charge of the two beta particles. And so it's going to create more interaction with the gas that it's moving through. It's much bigger, it's larger, it has a bigger surface area as it's moving through. It also has a much higher charge. It's a positive charge, which means it's going to attract any negatives. And so it's going to be observed to produce a bigger track because there are more interactions. In fact, when we look at the ionization of positive charges, alpha particles do lots and lots of damage, but they don't travel very far through an object because of this strong interaction or this high rate of interaction. Okay, the beta negative particles, well, these are going to have a negative charge. So it's got a negative E, which means I'm going to use my left hand rule. So whereas my alpha particle using my right hand rule went clockwise, let's put that on there, this one will go counterclockwise. So the left hand rule means it's going to go counterclockwise. It's also got a much smaller mass. So the decreasing mass means that there's going to be a decreasing radius. We'll talk more about that in the next example. So this one is going to be track 2. Track 2. Okay, so this guy here is the, I'm going to put that as beta negative. Okay, I'll put my track 4 as my alpha. And since track 3 looks exactly the same as track 2, it means it has the same mass, but just the opposite charge. So that must be my beta. It's got the positive elementary charge. I'm going to use my right hand rule because it is positive, which means it's going clockwise. It's got a small mass, which is the small radius. And so this is track 3. Okay, so track 3 is my positron. There it is. And that leaves the photon, a little bit of a giveaway, that the fact that this is just representing an unseen track. We wouldn't see it. It has no mass. It has no charge. So you wouldn't actually see it. It probably, almost certainly, wouldn't produce a track in a cloud chamber. So we're going to represent that as track 1. Okay, so in the previous example, we sort of intuitively said to ourselves that something with a greater mass is going to have a larger radius of curvature because it has a greater state of inertia. It's harder for it to change direction. We're going to show that now algebraically with our statements, and this one is a comparison of basically two particles, particle 1 and particle 2, and we can see that particle 1 has this wider turning circle, and it's got this larger radius of curvature, and particle 2 is a tighter, smaller radius of curvature. So what we need to do here is think about this in terms of the charge to mass ratios, and we're going to show, using our algebraic statements, why a greater mass would lead to a larger radius of curvature. Okay, so first things first, we should be pretty comfortable by now looking at these magnetic fields and curving particles going through them. But just to reiterate from the beginning, when we do our F-nets, okay, and F-net is the sum of all forces, and in these particular particle accelerators, there is only one force. It's coming from the magnetic force, and there is an acceleration because we have a changing velocity, so this is ma, but it's a particular type of acceleration. It's centripetal acceleration. And so we can then get to the statement which we are used to using, hopefully by now, which is v squared m over r is equal to qvb. All right, our job here is to think about this in terms of charge to mass ratio. This is a commonly used term. It was initially used extensively before the actual charge of the electron was known, because it could be used as a ratio in ways that could be compared effectively. So we're going to think about just the charge to mass ratio, which is, of course, if we were to just put that in algebraic terms, charge to mass would just be Q over M, charge to mass. That's the charge to mass ratio. And hopefully you can see that we have these values in this statement. So it's just a case of rearranging it to solve for Q over M. Let's go ahead and do that. So solving for Q over M, well, that's going to be Q is over M, just like this. And then we're going to have the velocity is going to cancel, the square is going to cancel there. So we're left with V over RB. Okay, so our charge to mass ratio is equal to V over RB. Now, what's important in this setting is that the velocities are the same. So these can be considered to be constant values. So we're just going to replace them with ones. Velocity is a 1 because it's constant. We've just made that number up. The radius is going to change between 1 and 2 because you can see that they have different radius of curvatures. So I'm going to keep that as my R. And then the magnetic field we're going to assume to be constant as well. So that's also going to be a 1. So I'm just going to ignore it. So you can see here that the charge to mass ratio, let's restate this, the charge to mass ratio of a particle moving in a magnetic field, uniform magnetic field, is proportional to 1 over R. In other words, it's an inverse relationship. If the charge to mass ratio goes up, then the radius of curvature will go down. In other words, if we were to just show this, if this goes up, and when I mean this, I mean the charge to mass ratio in its entirety, so let's just put that in brackets there. If this goes up, then the radius will go down. Okay, so that means when you're thinking about protons and electrons, which we might be doing in this example, in fact, I could just go ahead and guess that this might be the proton and this might be an electron. In fact, this would work with the hand rules because the magnetic field is going into the page. So for my proton, I would have a push upwards, and for my electron, a push downwards. But thinking about the masses, the mass of a proton is significantly greater than the mass of an electron. And so if we think about what that means in terms of dividing by these masses, the charge to mass ratio, if I think about this as the mass of the proton compared to the charge to mass ratio of an electron, given that the Q's are the same, so the Q of a proton is the same as the Q or the charge of an electron, then all I'm doing here is I'm dividing with the proton, I'm just dividing by a much bigger number. In other words, this is going up, whereas with the electron, this is going down. And so that means, because I have an inverse relationship, that this relationship here, if the mass of the proton goes up, what has to happen to the radius? Well, that also has to go up. So this shows you that if you increase the mass, which you do in a proton when compared to an electron, as this goes up, so does the radius. And so with my proton, if I'm considering my proton here, not my proton, my electron, this is proportional to a decreasing radius. Okay, so this is algebraic proof. If we make this initial statement about the forces acting on charged particles as they move through a magnetic field, we come up with this inverse statement. And if we get into what that means in terms of changing the masses, we can see that it affects the radius in an inverse way. Okay, so for our last example, we have some numbers and we have to do some quantitative analysis. This one's on a cyclotron. So just to get familiar with the cyclotron a little bit, it's basically parallel plates in the middle, right here and here, except we have an alternating current. So if you were to put a charged particle between the two parallel plates like we have here, it's going to be initially attracted or experience a force towards the oppositely charged plate, this way. So at this moment in time, this acceleration will be caused by a negative charge on this side of the plate. Now, the other bit of a cyclotron is that these hollow chambers are called Ds because they look like the D shape, and they're hollow and they have a uniform magnetic field such that the charged particle entering this region will experience a force magnetic which produces a circular motion. So this charged particle will then be curved around and it will come out of this side of the D heading towards the left D. At this point, the timing of the alternating current is such that this side of the parallel plates, if you like, is now negatively charged. So it's switched. It's gone from being negatively charged here, now it's negatively charged over here, which at this point will increase the velocity of this particle because it's entering this gap here in between with the velocity, which it acquired from this acceleration here. It's now going to experience an additional force. So work is going to be done to accelerate the particle even more. So when it gets to this point here, it's going even faster. And that means that the curvature here is going to be greater because it has a greater velocity. And it curves around here. It now enters the gap between, essentially between the parallel plates, at which point the alternating current has switched again and it's accelerating the particle again, and then again, and again, and again. So at each time the particle enters the gap between the Ds, it experiences an acceleration and it speeds up. So at this point here, it's going quite slow. At this point here, it's going even faster. It's going even faster, even faster, even faster, faster. And so its maximum speed will now be, as it leaves, well, the velocity here, this will be the same. So this V max is the same here, this V max. It's going the fastest it can possibly go as it leaves the cyclotron. And that's why this end piece is missing. There's a gap, so it can now leave the cyclotron and hit whatever you want it to hit. Why do you want to do that? Well, that's particle physics. If you want to know what something is made of, you smash it to pieces. And that's essentially what particle accelerators do. They smash things together and see what comes out. But this question is really just about this accelerator piece. We're told the magnetic field, and we're told the maximum radius is 20 centimeters. So in other words, the radius, which would be the greatest radius from here to here, this is the radius max, okay, because that's when it's going its fastest, so that's going to be the biggest radius. Now we need to know its speed as it leaves. Okay, so at this point, it's really just a straightforward curving of a particle, or the centripetal motion of a particle in a magnetic field. So we would go from the beginning, we'll do our Fnet expression. Fnet is the sum of all forces. Because it's going in a circular motion, there's only one force acting on it, and that would be the force magnetic. there is a change in the direction. In other words, there's a change in the velocity, even though the speed is staying the same. And I'm referring to only this last curvature here. In fact, maybe I'll make that really clear. I'm only now referring to this curve. Okay, the rest of the curves I'm not interested in because the speed will have changed for each one of these. Remember, it's accelerating each time it passes through here. It's accelerating, and I'm only interested in the maximum one. That's what the question is asking for. Maximum radius, which means maximum speed. Okay, so I'm only interested in this green curvature here. And so I am going to say that this is a straightforward circular motion. So it's mass times acceleration, except it's centripetal acceleration. So that means v squared m over r is qvb. The square and the velocity cancel out. And so I'm left with a velocity that is qb r over m. Okay, so let's put those values in. What do I have for my q? Well, it's a proton, so it has one elementary charge. So 1.6 times 10 to the negative 19 coulombs. My magnetic field is given in the question, 1.9 teslas. And the radius of curvature is 20 centimeters, which is 0.20 meters. And then I'm dealing with a proton, so the mass of a proton is 1.67 times 10 to the negative 27 kilograms. And that's going to give me a velocity here as the particle leaves the cyclotron of 3.6 times 10 to the 7 meters per second. That's two significant digits. Those in IB, it's worth noticing that this is actually 12% the speed of light, which we would get a little bit twitchy about because anything over 10% the speed of light, we start thinking about relativistic effects. But for this purpose of this question, let's not worry about that. And there we go. That's how we would do our cyclotron questions.